I'm going to focus really on the case of stochastic immersed boundary methods. And what's really motivated a lot of my work is trying to think about how I can apply immersed boundary-like ideas to obtain tractable and efficient, computational methods really for microscale mechanics. And so this has been motivated a lot by thinking about techniques that would be helpful in simulating how sort of microscale interactions result in more emergent kind of larger scale mechanics in problems like soft materials, which are obviously quite important to many biological systems that can be viewed from that vantage point. And I'll say a little bit about what soft materials are in a moment. Complex fluids, which have many interesting engineering applications, and then also other application domains. I'll talk a little bit about like protein diffusion within lipid bilayer membranes, where you're not only going to deal with the issues of things like thermal fluctuations, but also the issue that that the hydrodynamics potentially occurs in a 2D fluid interface, where there's also challenges related to the geometry. So I'm going to try to cover a sort of broad collection of areas, and then I'd be very happy to continue discussions if some of these subdomains are of interest to you, offline, as I was mentioning before. So please do feel free to reach out to me if any of these particular areas are of interest to you that you hear about in this talk. So the interesting about soft materials and complex fluids is that the microstructures, their interaction energies tend to be on the same order of magnitude as the thermal fluctuations. And so that has all kinds of really interesting implications for the mechanics of these systems, since many of the properties that ultimately emerge occur from kind of rearrangements of the system that often happen on much more rapid timescales than maybe the timescale in which you're observing the mechanics. And there's really, the behaviors that you're seeing are often a balance between not only the interactions that you've directly put in, but also kind of entropic effects, basically those rearrangements that were due to the thermal fluctuations. And in this sort of process, especially if you think about something like, I'm showing a colloidal fluid here, or you could think about a complex fluid of polymers. When you shear the system, the solvent also often plays a really important role. So in other words, hydrodynamic coupling will often lead to correlations in how these microstructures are going to rearrange in response to that external perturbation. And so you kind of have to capture, quite a few different effects that are occurring often at very different timescales. And so these problems are intrinsically quite challenging. And there's been a broad class of techniques that have been developed over the years to grapple with that, ranging from analytic models all the way through to molecular level simulation. And so probably the most obvious way you might try to go about modeling systems like this is to think about everything in terms of the atomistic level. And so, of course, molecular dynamics has been a very successful technique for capturing a lot of microscale, or even you could say nanoscale mechanical interactions. But the problem, of course, is you pay a big price because you're resolving sort of all of the atomic degrees of freedom. And so there's going to be very rapid timescales associated with many of the interactions. Now, you could also approach these problems from the continuum level, and that's also been successfully done for many problems. But the challenge, of course, in the continuum mechanics is you kind of have to formulate constitutive laws for your stress-strain relationships. And so, in many systems, that's not necessarily well characterized, and you'd really like to learn that directly from the microscale interactions. So there's been, a very interesting collection of work that kind of try to bridge these two domains, namely various types of coarse-grained models where you don't represent every atomic degree of freedom. You kind of maybe lump them into sort of mesoscale beads, have sort of, related mesoscale interactions. And then you kind of simulate the system, trying to just capture the sort of essential features or aspects of the mechanics that sort of mechanistically, capture what you think is going on in the microscale domain. Now, what's interesting there is, again, if I'm doing this in the context of something like a complex fluid, or where the fluid mechanics is playing an important role, that can also be very expensive because you have to in some way account for all of those solvent degrees of freedom. And so there's sort of, two ways that people go about these coarse-grained models. They might just model the solvent explicitly as their own coarse-grained particles, or they kind of just get rid of the solvent altogether and kind of fold it into the potentials, essentially the free energy potentials of interaction between the coarse-grained particles. Now, what's interesting here, though, is if I'm, again, looking at a complex fluid, that sort of removes, at least from the kinetics, the hydrodynamic interactions if I treat things implicitly. And so one of our goals has been to say, okay, if you do this implicit solvated coarse grain model, you may have captured the role of the solvent in the microstructure interactions, but you sort of don't have it in the dynamics or kinetics. So can we reintroduce that by basically building a hybrid model that has particle degrees of freedom for the microstructure mechanics, but then has a continuum theory that accounts for the contributions of the solvent mechanics, namely at the level of capturing things at the level of hydrodynamic equations. So anyway, this helps grapple with some of the challenges, but I really just want to emphasize again that depending on the particular problem you're trying to solve, really the issue is trying to grapple with phenomena that often spans really wide temporal spatial scale. So you have to be very judicious about what degrees of freedom you're going to sort of keep and retain in your simulations, and which ones you're going to try to either fold into the free energy or into some other aspect of how you're modeling the kinetics. So I got very interested in this kind of problem area, and I think the immersed boundary method provides a really nice way of effectively developing dynamic thermostats for these types of coarse grain models that can capture the hydrodynamics in a quite computationally tractable manner. And I'll explain some of the technical obstacles to sort of make that work in practice. But anyway, just want to motivate kind of that larger set of applications that we're really trying to target with these simulation methods. So as I said, the simulation aims really are if we can remove a lot of these degrees of freedom, modeling them explicitly and fold them into things like a continuum theory or coarse grain particles, it really lets us access much larger spatial and temporal domains, which then allow us to study much wider classes of phenomena. And so that's sort of going to be a big motivation for a lot of the approximations and the overall kind of drive in how we're going to develop a lot of these different stochastic immersed boundary techniques. Okay, and then there's all kinds of other potentially interesting domains that you could also look at, such as various types of active materials. You could look at collective dynamics of things like swimming bacteria and so on. So there's quite a wide range of phenomena where you really do want to capture sort of the microscale mechanics well, often subject to thermal fluctuations. Okay, so I'll talk a little bit more about background in a minute, but again, just kind of wanted to motivate that overall set of target applications. Okay, so I think I'll just move forward from there. And so we're kind of trying to target this kind of middle temporal, kind of length scale, if you want to kind of think of it as a sort of gradation of different levels of resolution in space and time, starting with fully sort of atomistic simulations and kind of working your way back up towards continuum. We're kind of trying to be right at the sort of boundary between where continuum models aren't quite there to get the job done, but these are things that if you were to try to do a bottom-up approach, starting fully atomistic, it would just get prohibitively expensive to try to simulate. So we're really trying to target ways of enhancing in some sense these coarse-grained sort of modeling approaches. Okay, so let me just say a little bit about our strategy of trying to use continuum level theory to model, sort of fluid mechanics at very small scale. But again, we're really at that sort of boundary where continuum mechanics is starting to break down. And what's interesting about that is it means that we're not only going to have to account for momentum transport through the usual sort of mechanism, when you have shearing in the fluid, if you think about a Newtonian fluid, you would have momentum transport within the material from that shearing motion. Well, if we get down to scales where the continuum hypothesis is starting to break down, there's going to be spontaneous momentum transport from basically collision events that occur between the molecules spontaneously due to thermal fluctuations. And we basically want to capture both of those things in a self-consistent way. Now, if you're not familiar with Brownian motion and these small scale systems, I'm just showing a little movie here on the left, just kind of illustrating, how Brownian motion originates. And there's a sort of long history, going back to Robert Brown in the 1800s, who observed this phenomena. It was kind of mysterious to them at the time. He was looking at pollen granules. And then, it was people like Einstein in the early 20th century that came up with an explanation showing that Brownian motion really seems to be a manifestation of the discrete nature of matter. This was still during the time when people were sorting out, atomic theory of matter and so on. So this was an interesting point of evidence. And then there's been a lot of mathematical and physical modeling and analysis of Brownian motion with Langevin, Smolchowski, Norbert Wiener, and so on. So the basic phenomena of Brownian motion arises because even if I put a sphere in a fluid where I'm not applying any external shear, what will happen is that sphere will diffuse around because of a sort of breaking of symmetry that occurs in the particular fluid at this scale, where sometimes you'll have more water molecules hit one side of this sphere than another. And so this little particle basically will for the for an instant basically have an imbalance in its momentum, and it'll start to move. And then that process will kind of repeat itself. And so this leads to this spontaneous motion that was observed by Robert Brown. And so what we want to do in our modeling is we essentially want to replace all of these detailed solvent degrees of freedom, all of those collision events, with some type of effective continuum theory. And so the motivation is what we'd like to do is somehow come up with a continuum theory that can capture the usual hydrodynamics that we're familiar with, but also include momentum transfer that can occur spontaneously because of, again, those collision events that I was mentioning. So the aim here is going to be to replace sort of this background, detailed molecular, mechanics or simulation with some type of, appropriate continuum field that fluctuates. And due to results like the central limit theorem, it's very natural to consider Gaussian random fields. So essentially, every location will be a Gaussian random variable, but the challenge then becomes to find the appropriate correlation structure so that, again, you are capturing this kind of spontaneous transfer of momentum. So one of the interesting things that will emerge from this is we're going to have random fields where there are fluctuations, but the momentum actually, if you were to integrate it up over the entire domain, will actually remain constant. So it's essentially going to be spontaneously kind of pushing momentum around in the system. And what we want to do is do this in a manner that's consistent with statistical mechanics. And I'll kind of show how we derive those correlation structures in a little bit. Okay, so just related to these ideas, I want to mention some classical work that was done by Landau and Lifshitz. And so they originally were thinking about similar ideas in the context of looking at, well, anyway, I don't go into all the statistical mechanics there. But anyway, they had developed similar ideas and introduced what are called fluctuating hydrodynamic equations. And the idea here was to take the usual Navier-Stokes equations, so the usual material derivative on the left, the Newtonian stress tensor here, the Lagrange multiplier for the incompressibility. And now the novel part that they introduced into the equations was the divergence of this random stress sigma. Okay, and so then the idea is that they can try to capture these the spontaneous momentum transfer through this random stress, and the random stress that they introduced is Gaussian with the following covariance structure. And so it's basically 2 times whatever the strength of the viscosity was in your original Newtonian fluid, the temperature of the system, kBT is basically the thermal energy that I was referring to, and then you have this sort of component-wise correlation structure, and I'll explain a little bit where that is derived. And then there's a delta correlation in space, a delta correlation in time. Okay, so that's the basic Landau-Lifshitz fluctuating hydrodynamics. Just a few comments that I want to make about that is, so you can go through principles from statistical mechanics, which again, I'll discuss in a moment, and you can derive this, but this leads to a number of challenges. I mean, number one, if you look at this closely, you all of a sudden realize that you're no longer kind of in the realm of nice, smooth functions when you're trying to solve the Navier-Stokes equations, because the sigma here is basically a Gaussian random variable that has delta correlations in space. And so this is really, in some sense, a random variable that lives on a space of distribution. So that's kind of challenging from both the point of view of analysis, as well as if I'm going to try to develop numerical methods for these types of equations. And I'll discuss a little bit about how we're going to deal with that in a little bit, essentially by introducing new types of stochastic forcing terms that take into account some of the numerical artifacts that come up in your particular discretization scheme. Effectively, it'll be a way of kind of regularizing the system, but in a principled way so that we can preserve certain types of statistical mechanical structures. Okay, and then the delta correlation in time causes the usual kinds of challenges for time integration schemes that you see when dealing with stochastic differential equations. So I just kind of want to point out again that there's significant differences in how you go about treating these systems numerically, and even in some of the analysis relative to maybe some of the other things that you've seen in computational fluid dynamics. Then there's the other challenge, of course, that how do we introduce fluid structure interactions in a way that is going to be kind of, again, principled with respect to statistical mechanics and also computationally tractable in some way. Okay, so that's going to be a lot of what I end up addressing in the first part of the talk. And then, of course, I'll show you, how we address some of these challenges and some of the simulation work we've done in this domain. I guess I won't say too much about this. I usually just like to motivate a little bit kind of the, the Reynolds number kind of regimes that we're interested in, and just kind of point out that there's been a lot of beautiful work done in the field of fluid structure interactions, in particular leveraging ideas related to immersed boundary methods. I particularly like this work by Song and al, where they've done simulations of hummingbirds and looking at hummingbird lift coefficients and so on, using this intricate immersed boundary model. There's also been great work done by Laura Miller as well, I should mention, on insect flight. And these are really targeting, the high Reynolds number regime. And then there's, of course, the work of Charlie Peskin, Boyce Griffith, and others on doing blood flow, interaction with the walls of the anatomy of the heart, which has been really great. Kind of, I would think of this as being kind of an intermediate Reynolds number, and we're really targeting this kind of microscale domain of really relatively small Reynolds number. So you might be tempted to say, okay, why not just do things in a completely overdamped manner, where you don't have any fluid dynamics at all? But there are experimental systems, especially when you get into dynamic scattering data sets of various types, where inertial effects could potentially be of interest. And also, it turns out from a sort of numerical point of view, there's often certain advantages when you're interfacing with molecular dynamics from the point of view of stability and numerical methods development, where keeping some of the inertial effects actually has some computational advantages we're finding. So anyway, so I'd be happy to talk a little bit more about some of those subtleties offline, but just kind of, again, want to contextualize the work that we're trying to do in kind of the domains that we're trying to target. And so there's many approaches in computational fluid dynamics by which you could go about coupling your microstructure to the fluids. Maybe the most natural way to do it would be to have two materials models. You could think about something like an airplane wing that I'm showing here. You have the fluid flow. You could use, your equations or constitutive models from elasticity for the wing. You could have your fluid mechanics in the external domain, and then have a traction stress at the surface that basically tells you how one material is acting on the other, or kinematic boundary conditions such as no slip. And that's, of course, widely done. Of course, you do pay a certain computational cost for doing that. You typically need to have, boundary fitted meshes. And you need to do remeshing often if the microstructure deforms significantly. So that can be done to get very accurate results at the fluid structure interface, but it does come at sort of this cost. And there's been a lot of work done in the finite element community on that and in other domains, and that is important for certain problems. Now, of course, when we start getting into the microscale, even exactly what those boundary interactions should look like, if you have discrete solvent at the surface of a polymer, starts to get a little bit tricky, right? And whether it really does adhere to what we think of as the sort of fluid structure interaction at the macro scale. So I think there's some preference for coarse graining this, not only because this is computationally expensive, but because it may be appropriate to come up with more approximate models for the fluid structure interaction that may account for things, like maybe hydrophobicity leads to a slightly different type of boundary condition than a molecule that is very hydrophilic and so on. There's also the ability to remove, in some sense, the fluid dynamics and derive effective hydrodynamic coupling tensors. And that's, of course, been done in the CFD community quite effectively, particularly in the field of looking at colloidal physics. And so you could essentially look at what the balance is between the fluid stresses and any forces and torques that you apply on your particles and derive pairwise hydrodynamic tensors. And that works quite nicely for many problems, especially where there's a lot of symmetries. Just pointing out work by John Brady, Gomper, and others. They've done all kinds of interesting simulations of colloidal systems, red blood cells, and so on. One of the challenges there, again, is it does rely on you having symmetry, so you can kind of tabulate these tensors often in advance. And you do kind of get into the issue of having a kind of n-squared algorithm where you have to do all pairs. And so actually some of the acceleration algorithms related to coupler tensing actually use ideas very closely related to immersed boundary methods, where they will actually map their particles or colloids to an underlying lattice and then compute there ultimately get the interactions. In cases like in a fluidics device or other complex geometries, you can see that this does become challenging. But I kind of, again, want to contextualize this because you're going to see that some of the techniques that we introduced in various asymptotic limits can be viewed from the perspective of some of these other coupling methods. So you can relate immersed boundary methods actually to these other approaches depending on how you take the resolution of the microstructure versus the underlying fluid. And so sort of in the immersed boundary method, you take this Eulerian-Lagrangian approach to modeling the fluid structure interactions. Here I'm just showing a few different examples, a point particle, a polymer, and an elastic body. And you kind of have these operators, and this is, again, from my perspective, the way I've abstracted it. I think about this operator gamma as being kind of similar to those kinematic boundary conditions that you have in the boundary coupling. It's telling you in some sense how the microstructure is going to move in respect to the underlying momentum field, or in this case, the fluid velocity. And then lambda would be a way that we're going to basically account for changes in momentum that are induced by the local microstructure. So the way that I like to think about immersed boundary methods is it's really like you have a hybrid heterogeneous material, right? And part of the material, of course, is fluid-like. Part of the material is elastic-like. And then those immersed boundary markers are kind of helping you to figure out, in which part of the material you're operating. And so I think of these lambda and gammas as being those operators that, again, account for how the forces and torques influence the fluid, changes in momentum, and how gamma sort of tells us we should move those effective material markers, essentially to track the configurational degrees of freedom. And so you can see that if you do take immersed boundary methods with sufficient number of markers, enough resolution, you can recover some of these other domains that I'm showing on the left. And you'll see this play out in some of the asymptotics that I introduce later. Okay. So let me say a little bit about background in statistical mechanics and stochastic analysis that I'll just need for the purposes of developing some of the core concepts related to these stochastic immersed boundary methods. And so this is a little technical, but I feel like if I tell you about this stuff, either it's a refresher for people that know it, but if you don't know it, this is definitely, in my opinion, some interesting results worth learning about if you want to work in this domain. And I'll try to just boil it down to what I see as the bare essence of what you would need to have some of the foundational ideas for stochastic immersed boundary methods. So the first thing is a lot of the modeling work that I'll be doing in the systems that I'm interested in will be primarily looking in the scenario where we basically have explicit degrees of freedom that we're modeling in the microscale mechanics. And there's sort of, if you like to think about it this way, hidden degrees of freedom that we're not modeling. And so you can think about that as effectively being like a heat bath. And so if you work with molecular dynamics, we're basically going to be in this NVT ensemble where there's this heat bath. And you can think about the heat bath in my case as effectively being all of those degrees of freedom of the solvent that I'm not explicitly resolving. So, if I'm doing a continuum theory, my Fourier modes are really capturing kind of the large scale collective motions of the solvent, but there's going to be all those microscale collisions and things that are coming from more intricate physics that I'm really just not, capturing in that continuum theory. So we're going to treat that effectively as our heat bath, and that's really, in some sense, what those stochastic forcing terms are accounting for. And so if you want the system to, correspond to, this thermodynamic conditions of having constant number, constant volume, and being at a constant temperature, that's going to be have the following probability distribution associated with it. Basically, you're going to pick the probability distribution which maximizes the entropy subject to those thermodynamic constraints. And so what that amounts to is finding over my microstructure degrees of freedom. That's including, in this case, the fluid mechanics and the actual structures, polymers, colloids, what have you. You're going to find the probability distribution which maximizes the entropy subject to the condition that the average energy remains constant. And so if you solve that variational problem, it turns out that the probability distribution you get is the one that I'm showing here, which is known as the Gibbs-Boltzmann distribution. And so whatever my energy along the states of the system X, and states here I mean quite generally, this includes both the configurational and the momentum degrees of freedom, is going to be given by this distribution. So it's just basically going to say that if you were to just observe the system at any given moment in time, the probability that you would see state X would be proportional to the inverse exponential of the energy of that state divided by kBT. Okay, so this is how the the effective temperature is going to come in into the model. And then this Z that you see out front, this is effectively, this is a very important quantity if you're doing statistical mechanics analysis. But you can think about this Z, which is called the partition function, as effectively normalizing those weights. But like I said, that's often playing a very important role, especially when you're computing various types of free energies and entropic contributions and so on. Okay, so that's the basic target probability distribution that we're aiming for in our stochastic modeling. Is if we want to capture the mechanics correctly, we at a minimum need to get the right equilibrium behaviors, and this would be the probability distribution that should govern what occurs in the relative frequency of states. Now, there's another thing that I'm going to leverage throughout my modeling, and that is the fluctuation-dissipation principle, which manifests in many different ways. But if you boil it all down, what it's really saying is that if you see a spontaneous fluctuation in the state of the system, we're going to assume that spontaneous fluctuation relaxes back down in some sense to equilibrium, the same way as a small externally induced perturbation of the system would relax. And so that way there's kind of like a symmetry here. If the system spontaneously changes state, it's going to kind of dissipate energy or relax back the same way as if I impose some external field. You could think about like a magnetic field or something along those lines. If I were to perturb the system from its natural resting state, and then I turn off the magnetic field, everything relaxes. That tensor showing how things relax, we're going to assume is the same type of relaxation I would see if I spontaneously achieved the same state through an internal thermal fluctuation. So that's going to be an important symmetry because it allows us then to leverage our constitutive laws appropriately. Otherwise, you would have to go back and reference some kind of molecular level model in order to do your modeling. Okay, so those are sort of the key ideas from statistical mechanics that I'm going to leverage. And then, in order to build my model, we're going to use the language of stochastic differential equations. And so stochastic differential equations, in some sense, are very closely related to things like ordinary differential equations, but with a small twist. And the twist is that we're going to have our ordinary differential equations essentially have a randomized forcing through some kind of stochastic process. And this is going to be a rather special forcing, but closely related to the idea that we're making assumptions that the forcing terms are essentially Gaussian in time and have various types of correlation structures. And so it turns out that a very wide class of those types of models can be written and expressed as in terms of a usual kind of ODE, where A here is denoting the drift of the ODE. And I'm writing this in differential form as opposed to a differential equation because we'll see that these increments, or it's known that these increments of Brownian motion basically scale like square root of dt. And so you can't technically take derivatives, but you can carry out a lot of the calculus using essentially integration type expressions. And I'm not going to go into all of the details there, but I just wanted to motivate why I'm writing things in this form. But basically, the idea is that we're going to take for our forcing terms that they're always some type of linear combination of increments of Brownian motion. And if you're not familiar with the Wiener process, this is the mathematical realization or model, if you like, for that Brownian motion I showed you in the beginning in the overdamped regime, where it's basically just a stochastic process, which if you take the difference at 2 times, time 1 minus time 2 minus time 1, it's always going to be, the increments are always going to be Gaussian random variables of mean 0 and variance the time duration, t2 minus t1. And so you can show the existence of such a process. You can go through that and construct this probability measure on the space of continuous functions. And so that's a bit of work. And so what we're going to do is we're going to leverage that to then express this whole class of models as effectively transformations of that sort of reference Wiener process. And that's the idea of stochastic calculus. It captures a very wide, you can capture a very wide range of phenomena this way. Okay, so effectively this term, though, when you boil it all down, is just going to be a stochastic forcing term, which is Gaussian and has a certain covariance structure among its components, and it'll be delta correlated in time. So it'll start to have a lot of those properties of what I showed you when I looked at the Landau-Lifshitz fluctuating hydrodynamics, for that random stress. It's going to basically be something that allows me to capture objects of that nature. Okay, so the B here is essentially going to be what captures my spatial correlation. So think of all of what I've written here as being vector valued quantities. Okay, and then I'm going to take the Ito interpretation of stochastic calculus throughout, as opposed to the Stratanovich one. You could always convert a lot of what I'm doing into that setting. Okay, so if we take, if we look at stochastic differential equations as being our class of models, there's a really important transformation that I just want to raise your awareness of, which is if I do a change of variable, there's a slight difference in the context of these stochastic models relative to what would happen for an ordinary differential equation. So, so again, think of my x, this is all vector valued, the xt's, that's in Rn. I'm going to think about doing a change of variable, or if you like, a projection to a new variable yt, which for now I'll make it scalar just to keep the math simple to express. And so let's suppose that yt, you could think of it as an observable, or you could think about it as some type of change of variable from my original stochastic process xt. I'll assume that f is twice continuously differentiable. Then the question becomes, what equation does the yt satisfy? And so if you were doing just regular, ordinary differential equations, you say, okay, that's easy. I just do the chain rule, right? You just do derivative in y, well, I do the derivative of the outer times, dx dt, and I'm done. Not the case in stochastic analysis, and this is where you have to be really careful because it's really important. Otherwise, you're not going to capture the appropriate physics. You get all kinds of artifacts in numerics and so on. So there's what's called the Ito lemma, and it's kind of one of the workhorse, sort of lemmas that you use when doing stochastic analysis. And what you basically have to do is expand the process yt out to second order in the original process xt. And the reason for that intuitively is that if you look at increments of Brownian motion, I had told you that the variance of increments goes like the time duration. So that means the standard deviation goes like square root of duration. So that means that effectively this dwt is kind of like a square root of delta t. And so that means that you do need, the second order term, right, in order to capture everything up to order t in the expression of the new equation. Now, there's of course a lot of, probability that you have to do to kind of justify some of the rules that I'm showing you here, but that's the sort of rough intuition for why you have to do expansions to second order. Okay, so this shows that the new process would satisfy the gradient in f, dxt. This would be just like the usual ODE chain rule expression. But now I need to do this second order expansion, right? So this is the second order term in my Taylor expansion, just written in terms of these differentials. And then we do one other thing, like we would like to express ultimately dyt in terms of dt and the increments of Brownian motion, right? So we can get it back into kind of the standard form of an Ito's stochastic differential equation. And so the way we're going to do that then is to expand out what dxt is in both expressions here. Now, you're going to have a lot of cross terms in this second expression, right? So the first one's pretty easy. You'll get a dt, you'll get a dwt. So you see down here, you recover that dt, you recover that dwt. It's this term where you have to pay a little bit more attention. And again, I won't be able to go into a lot of the technical reasons for this, but if you have the cross term dwt I and dwt j, that'll turn out actually, if you were to do this discretely and kind of take a limit as delta t goes to 0, you would actually find that this increment squared would actually start to approach essentially a Dirac delta centered around dt. Okay, and it takes a little bit of analysis to go through those details, but it's essentially a square of a Gaussian, and you can show it has this property. So that means that actually, as you take the delta t limit to 0, that this actually becomes just like the differential dt. And then, of course, the components are independent, and so you get a little Kronecker delta ij there. Okay, so that's going to be how we treat the differentials when they interact with each other in the Wiener component. And then the other stuff all comes in higher order. You have dt squared, that's higher order than dt. dt, dwt, that's roughly speaking like something on the order of delta t to the 3/2, and so that's higher order than dt. So you set those formally to 0, and that's how I arrived at this final expression you're seeing at the bottom. So in a nutshell, this is the idea of the Ito lemma, that we can do changes of variable with stochastic processes, but we just have to do our bookkeeping carefully to take into account those extra contributions that come from the irregularity in some sense of that little stochastic forcing term. So the upshot of all this is that it contributes an extra term to the drift in the final expression for the process. So you're going to see this come back, and this will have some really important implications for some of the results that that we end up leveraging in this modeling. Okay, so what I'm going to do is putting some of this together now. This provides some important modeling principles that I can really leverage to take some of these abstract ideas related to statistical mechanics and start to really actuate on them in the context of deriving things like appropriate stochastic or thermal forcing terms in my hydrodynamic equations and in other forms of modeling. So what I'm going to do is I'm going to use the fluctuation-Dissipation principle and combine that with this Ito lemma result effectively to show that if I have a linear stochastic process, so L here you can think of as some negative semi-definite operator, or matrix if you like for now, or if I have a linear stochastic process like this, the question often arises, how do I stochastically force this so that I achieve the appropriate equilibrium statistics? And so if you know, for example, that your equilibrium statistics should be given by the canonical ensemble, in the case that your energy was quadratic, and so what I'm showing here is that the energy is 1/2, whatever the state of the system is, this matrix C inverse X, it turns out that if I look at what the canonical ensemble is for this, that's essentially just going to be a Gaussian, a vector valued Gaussian random variable that has mean 0 and has a covariance structure C. Okay, so that's what you would have if your energy were quadratic in the state. And if I have a linear stochastic model, as I'm showing here, with dissipative operator L, but I don't know how I should stochastically force this system, it turns out that I can essentially use the Ito lemma to determine that. And I get what are often referred to as the Nyquist relations, that this Q, in order for this dynamical system to have the appropriate target steady state distribution, that QQ transpose has to be equal to negative LC minus C transpose L. So what this allows us to do is basically leverage our knowledge about how those relaxations to external perturbations result, again, in relaxation of the system, and our knowledge about what the equilibrium probability density should be for the system to basically derive the stochastic forcing that we would need to appropriately model the dynamics within this, again, this linearized regime. Okay, so this is a really important principle that's going to allow us to sort out all kinds of issues with respect to not only the sort of continuum level modeling, but also when we start to develop various types of numerical methods for these stochastic immersed boundary approaches. Okay, so let me just talk a little bit more about that last result, because that's going to be so central to, again, the sort of foundations of how you deal with the stochastic forcing terms in different formulations of stochastic immersed boundary methods. Okay, so basically this is going to follow from the following. Let's look at how the covariance of xt transpose evolves over time. And essentially, let's write down an ordinary differential equation for this quantity. And so if we do that, we can use Ito's lemma, and we can show that the rate of change of the covariance structure is going to be given by the following expression. So what I've done here is just to kind of make the notation more compact, and you'll kind of see this throughout, we like to write expectations when we're doing statistical mechanics calculations as just angle brackets around the random quantity of interest. And so that's what I've done here. And so this is just XX transpose taking its expectation by definition. And so if I do that, again, the second order expansions in the Ito lemma, you can do this component by component. You'll see that it amounts to averaging the increment times XT transpose, XT times the increment transposed, plus the average of the increment, outer product with itself. And so then if I start to unfold what dxt is, which is given up here, this is Lx dt, Q dwt. You can see that the dwt and xt terms will basically give me 0. So the only term that's going to survive here is lxt. So I'll have lxt, xt transpose. Similarly for the other expression. And then this is the interesting one where the rules from Ito calculus really come through. You'll see that this will give me Q transpose times the identity because of the nature of how those increments in Brownian motion are treated. And so, okay, so what you end up with then is the following expression for how the covariance structure is going to evolve over time for this linear stochastic system. And so what's interesting about that is, okay, this is the final equation you get. And so now, remember what we're trying to do here. We have, certain pieces of information, such as we know what the equilibrium distribution should look like. In other words, what the fluctuation should look like at steady state. And we want to leverage that to figure out what the appropriate stochastic forcing is. And so what that amounts to then is saying, okay, well, we're going to have a certain steady state for the covariant structure. So that means that this dCt is going to go to 0. And if we want the steady state covariance to go to C star, or it goes to C star, then the following relationship has to hold between the covariance structure of the stochastic forcing and the dissipative operator, namely that QQ transpose has to be effectively negative LC minus C transpose L transpose. Okay, so this is going to be this is how this relationship arises. Essentially a consequence of Ito's lemma and the fact that once you have a linear stochastic model, there's really only in some sense one way, in a weak sense, to force the system to achieve those equilibrium fluctuations. Okay, so the consequence for modeling is that if you know the equilibrium fluctuations of your system and you know the dissipative operator, then effectively you can derive now the appropriate thermal forcing for that system. Okay. All right, so those are going to be the key results in statistical mechanics and stochastic analysis that I'll be leveraging throughout. Discuss next some of the fluid mechanics and how we're going to kind of pull all of this together. So I'm going to start off modeling things in a regime that's a little bit different than the traditional immersed boundary method, but leveraging similar ideas, which is I'm going to actually have two separate momentum equations, one for the fluid mechanics and then one for the microstructure degrees of freedom, and then we're going to couple those two things together. And again, we're going to do this in the context of these Eulerian-Lagrangian type of mechanics as is done in the immersed boundary method. And so just to kind of introduce the notation that I'm going to use throughout, we'll have that U will be the fluid velocity that you can think about as being this whole blue region that's described in the Eulerian frame. Again, like I said, I like to think about the immersed boundary method as kind of modeling like a hybrid material where the fluid equations are kind of doing double duty. They're accounting for the momentum of the fluid as well as the elastic bodies that are in the immersed in the fluid. And so that's very powerful because then you only need to computationally track one momentum field throughout, and all these wonderful computational advantages come out of that. I'm going to do it where now I have basically two momentum equations, and then I'm going to do something related to like a tight coupling that will ultimately reduce down to the immersed boundary method. But we're going to do it from this perspective because there are going to be some additional stochastic terms that come in, again, due to essentially the Ito lemma that will influence the final formulation of the stochastic immersed boundary method. Okay, so if we go from this perspective, the U here is the fluid velocity field. X of QT will be the structure degrees of freedom. I'll just be parameterizing a material point of whatever my structure is. It could be a point particle, it could be a polymer, or even a spatially extended elastic body. I'll label the material points by this abstract variable Q. But X anyway will be the location of that material point at time t, and V will be the associated velocity of that material point at time t. Okay, and then there's a few ways that I've abstracted things a little bit just to kind of, again, show the way that these interrelate. I'll be denoting the essentially Newtonian divergence of the Newtonian stress. I'll be denoting that by this fancy L. But you could use this this framework for other constitutive laws as well. This is just going to be whatever the dissipative operator is associated with the fluid. But typically that'll just be mu times the Laplacian of U. I'll have this epsilon parameter, which is kind of like a slip parameter that'll tell us how strongly the microstructure is being coupled locally to the fluid. And that'll eventually I'll take to infinity. We'll see some interesting outcomes of that asymptotic limit. Gamma here is going to be, like I said, this kinematic operator that kind of tells us how the microstructure moves in response to the surrounding flow. And then lambda will be basically the force spreading operator that tells you how any stresses, forces, torques ultimately will influence the fluid's change in momentum. Okay, so the way that we're going to model things then at this level of abstraction is the fluid equations. This is basically the usual Navier-Stokes equations, where you can think about this as being mu Laplacian u, but again, just for the nature of showing you kind of from this point of view that the only really important property of this term is that it's some negative semi-definite operator. I'll just denote it by fancy L. And then what we're going to do is take we're going to linearize the equations for the purposes of this modeling. So I've gotten rid of the u dot grad u, and again, I'd be happy to talk offline about some of the subtleties related to the asymptotic limits where that's an appropriate can be appropriately justified. Okay, so that's this is the fluid equations. The main thing to note about it is if I have that the microstructure is moving faster than this reference fluid velocity, so gamma u is the usual velocity averaging type of operation, there's going to be basically a drag that pulls the fluid towards the, in the motion of the microstructure, towards the microstructure. And then the lambda here, what it does is it basically takes that drag and it converts it to a force density using a force spreading operation. And I'll say a little bit what these lambda and gammas are in a moment, and you can make them pretty much anything you like, provided they satisfy certain basic properties like an adjoint condition. And so if you do the immersed boundary coupling, this would just be the usual averaging against things like the Peskin delta function. This would be things like doing the force spreading using things like the Peskin delta function. Then the lambda here, this is just a Lagrange multiplier for any constraints you want to introduce on the mechanics of the fluid body. Typically, when you do incompressibility, this would be the gradient of the pressure. And then the thermal fluctuations are really the term that I'm most interested in here. But that's an explanation now of our formulation of the fluid mechanics in this notation that I've introduced down here on the right. Okay, and then we're going to have the microstructure equations, and they're going to satisfy their own momentum equations. So we'll have basically the usual F equals ma. So ma is here on the left, and then the forces that the microstructure experiences is a drag if it's moving faster than the local reference from the fluid body, right? Because gamma is doing velocity averaging. V is the velocity of the microstructure. So if your particle's moving faster, there's a drag pulling it backward. And the strength of that drag, again, will be governed by this coupling parameter upsilon. And then if you have whatever your forces are that act on the microstructure here, I'm just writing them as conservative forces with this potential capital phi, that would also appear on the right-hand side of the momentum equation. Lagrange multiplier, again, you could also impose things like rigid body constraints on the deformations or the motions of the microstructure that would come in through this, this zeta term. And then again, what I'm most interested in here is what are the appropriate thermal forces. So the idea is that when we do the statistical mechanics, we don't want to do the statistical mechanics just thinking about an abstract continuum theory. We want to set up the continuum mechanics so it closely mimics some of the approximations, for example, of the fluid structure interactions that enter into techniques like the immersed boundary method, so that we're taking into account in sort of a holistic way not only kind of the fundamental mechanics, but also some of the approximations. Because if we don't do that, what can happen is we can get incompatibilities between how we thermally force the system and then how it actually behaves when we try to use it in practice with some of these approximations or coarse graining, if you like, of things like the fluid structure interaction. Because we're not doing traction stresses at the surface of the bodies. We're not doing kinematic conditions like no slip boundary directly. We replace that with these operators, gamma and lambda. Now, in various asymptotic limits, you can recover those types of properties, but it's really important to take into account some of the natures of that particular approximation that you're making when you introduce this F therm and capital F therm. And that's why we're not just saying, okay, just use Landau-Lifshitz fluctuating hydrodynamics and just put immersed boundary methods on top of that. We're really trying to, in a principled way, derive the stochastic forcing terms with the particular types of mechanics that immersed boundaries capture or model, so that everything is sort of done self-consistently with respect to those principles I mentioned before. Ultimately, when I spatially discretize, right, we know that the dissipation in a discrete operator describing a fluid, like central difference, is going to be quite different than the continuum Laplacian, and we will take that into account as well. So, okay. So I'm going to do it first at the continuum level, but we're going to do basically a very similar kind of calculation once we start discretizing these. And this gets particularly interesting when you have non-uniform discretizations, either like an adaptive mesh, or if you do something like finite elements. Again, it's going to be a little bit delicate how you introduce these F therms so that you appropriately balance the nature of the dissipation of those discrete operators versus their continuum analogs. Yeah.
Okay, and just as long as we are at the continuum level, is the spreading and interpolation done then with the true delta function, or are you regularizing those even though everything else is continuous?
Yeah, so that's a good question. So in fact, I'm allowing you to use pretty much any notion of gamma and lambda that you like. And so that's what I want to do the calculation this way, because I can kind of do the sort of work once, which is a little bit involved to get all the statistical mechanics right. And then after that, I can just start substituting different pieces in, depending on which variant of immersed boundary method and so on that I want to carry out. Yeah.
Okay, thanks.
So so they're not going to be true direct deltas. They can be something that has spatial extent. And I'll show a few examples of how we've leveraged different results in fluid mechanics to come up with different types of operators for not just point particles, but things that can undergo rotation and so on.
Okay, so the question.
Yeah, sure.
Sorry, yeah.
Yeah, no problem, yeah.
Yeah, I see there's a big lambda in the first fluid equation. Why is not show up in the microstructure equation?
Yeah, that's a good question. So one of the things you always have to remember is that the fluid equations, what appears on the right-hand side is force density, right? So it's going to be force per unit volume. On the right-hand side of the microstructure equations, at least if I'm modeling with point particles, those are just going to have units of force. And so what lambda is doing is it's basically converting a force, which is something that acts, let's say, at a point particle, to something which is spatially distributed for the purposes of accounting for it in the momentum equations of the fluid. So it's basically converting forces to force densities. Yeah. And that's essentially what happens in the immersed boundary method when you multiply your force times the kernel function, the Peskin delta function. Okay, so to leverage the concepts that I introduced related to statistical mechanics and stochastic analysis, we basically have to figure out what the energy of our system is, because that's going to ultimately govern the equilibrium fluctuations, and that's what I'm doing here. And so the energy of the system is primarily the kinetic energy of the fluid, that's the first term here, the kinetic energy of the microstructure, that's the second term here, and then the potential energy of the microstructure. And the potential energy here is not going to play as big a role because the places where there's dissipation occurring is, from an abstract dynamical system point of view, is really from the V equation and the U equation. Essentially, the momentum equations are the ones that are dissipative. The configurational degree of freedom doesn't have dissipation in it. Okay, so putting that together, we can also collect together the dissipative operators of the system. And so if you look, you're going to have dissipation through the Newtonian stress. You're going to have some dissipation that occurs from this coupling, the dissipation associated with the U degree of freedom of just collecting together lambda, epsilon, gamma. That's where this first operator came from. Now, if you want to write it in the form that I stated that previous fluctuation-dissipation relationship, I have to multiply these equations through by the density so that I get something just in terms of time derivatives of U, just in terms of time derivatives of V. Now, I could have gone through and reformulated everything in terms of momentum degrees of freedom, but the simple thing to do is to multiply through these row inverses, and then you get these operators. Okay, you're going to see that disappears when I go and introduce the covariant structure at the end. So it's natural to write things like I did above, but just be mindful of the fact that you do have to multiply through the mass and density terms to put things in the form that I had on the previous slide. Okay, so that's why L is written with these prefactors, just for keeping things precise. But you'll see that that'll ultimately those will ultimately disappear when I write out the final thermal forces in this form. Okay, so the Newtonian stress tensor is dissipative, the coupling is dissipative, and it contributes this term and this term in the first equation. And the second equation, again, you have dissipation occurring through that coupling, and that's given there with U. With V, you get the usual epsilon term. So this is just writing out the operator, which is going to describe all of the dissipation, all the sources of dissipation in our system above. Okay. Then what we're going to do is we're going to apply, the fluctuation dissipation principle that I derived for you to try to obtain what the covariant structure is for these thermal forces. And so what we effectively have to do is we effectively have to compute this operator, which is negative LC, negative C transpose L transpose. Okay, so in order to get what C is, we're going to go back to our energy here. And if we know that we're in the canonical ensemble, then that means that the fluctuations are going to be governed by the Gibbs-Boltzmann distribution. And so that has a probability density formally. It's really a measure, but we'll write it formally as density here. It's going to be something inverse exponential in the energy over KBT. And so the energy is what's given here. Now, if you look at this, it's essentially going to be a Gaussian distribution because our energy is quadratic in the U and V degrees of freedom, right? For now, let's not worry about phi because when I multiply everything together, the phi turns out that it's not going to play a role in how I introduce thermal fluctuations. So looking just at the first two terms, you see that this is quadratic in the degrees of freedom U and V. So that means effectively the Gibbs-Boltzmann distribution is a Gaussian random variable. And now what I need to do is just say what that covariant structure is for that Gaussian random variable. And so you can see immediately, because I only have terms U squared and V squared, the covariant structure is diagonal. And so what you end up with is the following operators formally that characterize the covariant structure, namely that you have delta correlation in space proportional to KBT and the rho inverse. And you have, again, a kind of Kronecker delta correlation in the components of the microstructure. Okay, and so that's coming out again from the Gibbs-Boltzmann distribution. And now what we need to do is put this together with LC, and that will give us our thermal forcing. And so if we put all that together, this is the thermal forcing now for these Eulerian-Lagrangian formulation of mechanics where we have these general coupling operators, gamma and lambda. So this allows us now to extend the fluctuating, the Landau-Lifshitz fluctuating hydrodynamics to incorporate now fluid structure interactions, where our fluid structure interactions can be modeled at various levels of approximation and styles, depending on what type of ultimate phenomena you're trying to capture. Okay, so what you see is that you get for the stochastic forcing of the fluid mechanics, you see that you get something proportional to L. That would be the usual Landau-Lifshitz fluctuating hydrodynamics, divergence of random stress. You see that you get here, because of the dissipation, you get this, this cross term that's going to depend on your force spreading operator and your velocity averaging operator. And then all of this is delta correlated in time. And because of the nature of how I'm writing these operators, there's also implicitly that delta correlation in space that we saw when we looked at the Landau-Lifshitz fluctuating hydrodynamics. So just be mindful, these equations are going to be a bit challenging in principle to analyze and solve because we will end up with fields that are quite irregular spatially. Okay, and then this is showing the stochastic forcing term for the microstructure degrees of freedom. For those of you that are familiar with Langevin dynamics, this should look familiar. This is actually the usual Langevin forcing that you would have because of the nature of the drag just being negative epsilon b. But there's a slight twist to this, which is that this stochastic force that comes into the microstructure equation is not just generated completely independently of what's going on in the fluid. In fact, because these two things are very closely linked, any momentum that I lose from my particle here through the drag is going to enter as a source term in the fluid equation, and vice versa. If the fluid happens to go be faster than the particle, it's going to drag the particle along, and momentum would then leak out of the fluid and enter into the microstructure. So unlike traditional Langevin dynamics, in fact, this kind of thermostating will be momentum conserving. So the momentum that you lose from the microstructure ends up in the fluid degrees of freedom and vice versa. And so as a consequence of that, you see that, in fact, the thermal forces that influence the fluid are actually correlated with the thermal forces that impact the microstructure. And this gives the precise correlation structure. It's negative 2 kBt lambda epsilon here. And again, all of this in our modeling framework is delta correlated in time. So that's quite interesting. So it means that even with the thermal fluctuations, basically the thermal fluctuations in some sense are moving momentum not only laterally, as I was mentioning in the beginning, between different parcels of fluid, but also between the microstructures in the fluid in a way that is ultimately momentum conserving. So you're basically just picking up momentum from one location, spontaneously moving it to another location. And the reason for that, if you really think back to the molecular level physics, is that all of these thermal fluctuations are ultimately coming from molecular level collisions, right? So there's parts of the fluid body that are molecularly colliding, right, with other parts of the fluid body. That's leading to spontaneous transfer laterally. That's what's being captured by this little f therm. But there's also, right, at the molecular level, collisions of the fluid particles with the microstructure particles. And that's leading to this cross correlation with F therm. And of course, within the microstructures themselves with the fluid leading to this F therm. So this allows us to self-consistently capture all of those different types of collisions and cross collisions in an appropriate manner at the level of these Gaussian random fields.
For Paul, I have a question about the thing you just said. So the equation is just an equation for the correlation. So the question is, when you actually implement this, do you get a detailed balance of the two things? Or I'm sorry, I don't mean in the sense of detailed balance in the technical sense, but I just mean,
I know.
Is it just a correlation, or is it an exact balance? I'm just curious which way it comes out.
Yeah, so no, I mean, if you go back to what I mentioned about the linear dynamical systems and those Nyquist relations, if you work it out, it does exactly balance all of the momentum in the system. Yeah, so it's not just capturing it to leading order. Yeah,
okay. So it's not just the expected value, but it's in more detail than that.
Yeah. So every realization, if you were to total up and track over time, the total momentum, that would be constant. Now, of course, that's with no external forces acting on the system and so on.
Yep. Okay.
Yeah. So that's a potentially important property. We've seen this in some of our soft material models, that you will get lateral propagation of momentum that is missing if you use something like a Langevin thermostat. For example, in the context of some of our coarse grain models of lipid bilayers and so on. So for certain problems, that feature could be quite important to get the right phenomenology. Okay, all right. So that's I understand that's a little bit abstract, but I wanted to lay down this framework first, because then all of these different cases become specializations in some sense of this calculation that I've done in detail here for you. Okay, so there's many ways you can do coupling operators, and I find this to be a particularly fun and interesting aspect of immersed boundary methods. And the one that you're probably most familiar with is the one that Charlie Peskin introduced in his early work, which is this really nice idea that you can capture fluid structure interactions essentially through doing this velocity averaging and force spreading using a sort of smeared out Dirac delta function. And then there was very nice work done deriving what an appropriate property should be for these kernel functions to get nice properties like translation invariance and so on to some good approximation. And so there's a couple of considerations that we need to take into account with these operators lambda and gamma. Namely, the lambda operator, we're always going to require that when we integrate it over the fluid body, that we get back the total force that we had applied to the microstructures. And so I think of that as saying, in some sense, the lambda operator, if you were to break it down into a kernel, that kernel essentially has to integrate to 1 is what that amounts to. So that's one very important constraint. Because on the previous slide, I basically said you can use almost any lambda gamma you like, but there's going to be a few generic properties that you need so that that they don't misbehave and give you weird results, such as additional channels of dissipation in the coupling. And so the other one is, and you can derive this other ways by thinking of notions of work, but if we think about in the overdamp limit where everything's tightly coupled, and we look at the rate of change of energy in the system, you can very naturally derive these adjoint conditions that basically say that the amount of work being done on the microstructure needs to balance with the amount of work that that is being done on the fluid. And what you end up with essentially coming out of this is that for these two terms, when you sum them up to be 0, amounts to rearranging here that the gamma, the velocity averaging operator, must in some sense be an adjoint of the force spreading operator in the sense that I'm writing down here. And I presume that you've seen this a few times in the inverse boundary course. So this is the notation that I'm going to use to express those adjoint conditions. So basically integrating over the microstructure material points, the velocity averaging is got to be equal to this inner product, which involves integrating over the fluid body. And this is going to be one of the key relations, and you'll actually see this come up in that covariance operator I had on the previous slide, because if you don't do that, you're not going to get symmetry in the off-diagonal terms in the dissipative operator. And so this is quite important that these don't introduce additional sources of loss or dissipation. Now, you could model in principle where it is lossy. Maybe there are physical scenarios where that's important. But if you did that, you'd have to rework some of the statistical mechanics I showed in the previous slide, just to take into account those additional sources of dissipation. So throughout the methods that I'll show you, we'll be assuming that effectively you have this adjoint condition on gamma and lambda. And so effectively, if you have this first property and this adjoint condition, you can be as creative as you like with gamma and lambda. And one of the things that I find particularly compelling about this is it basically tells you that if you know one of these operators, you can get the other one. And that's a very beautiful aspect, I think, of the immersed boundary method. So if I know, for example, how my microstructure should respond kinetically to the surrounding flow environment, now I can turn it into an active model by applying the adjoint condition and getting what my force spreading operator should be. And vice versa. If I have a very clear conception about how I think my microstructure should influence the surrounding fluid body, then I can also get the kinematic response by using the adjoints. So it's really great, I think, from a modeling point of view, and you can usually very readily compute these adjoints to get the appropriate mathematical structure for your system. And we've done this in a number of contexts, extending this to use things like Faxon relations, which talk about kinetic responses, or even building various types of immersed boundary methods on surfaces, so on manifolds where it's not quite as obvious how you should do the force spreading and velocity averaging. We basically use various types of reference fields and L2 inner products to create our kinematic responses. And then in return, we get appropriate force spreading operators and can capture things like rotational motions of proteins or translational motions in very intricate geometries while staying sort of in the tangent space in our velocities on the manifold. So you can apply these concepts quite broadly. Okay, so I just wanted to point out one thing that I found interesting, which was that again, I've been trying to kind of read and interact with different communities, and so one of the interesting things is the immersed boundary method. If you go through and you kind of empirically look at the Peskin delta approach to doing force spreading and velocity averaging, which I presume you've seen a lot of already in the course, and so in my notation, I would think of the velocity averaging, gamma u, as being this integral against this spread out Dirac delta, and this lambda as being the force spreading operator as being whatever your particle forces are times the spread out Dirac delta. You can show very readily that these satisfy the adjoint conditions. In fact, that's how they were originally derived. And so it turns out that you can go and look, okay, what is the pairwise interaction tensor that I get from this representation of the fluid mechanics? And so, we don't expect things like for two colloids to get lubrication effects as we get in the near field. We expect that to be regularized in some way. And that's fine, right? It's just, you need to just be aware of the mechanics of the model that you happen to be using. And so it just turns out that if you're familiar with what's been done in the polymer mechanics community, it turns out that the immersed boundary approximation is very closely related to the Rotny-Pragner-Yamakawa coupling that's been used in analytic calculations for hydrodynamic coupling in polymers. And so this is just showing quantitatively that effectively the Rotny-Pragner-Yamakawa tensor quantitatively is very close to what you would get if you use the Peskin delta functions in the immersed boundary method. So I just computed the pairwise hydrodynamics. The blue curve here is the Oseen tensor. Obviously, that's a bad idea in the near field because that blows up like 1 over r. But if you use RPY, you can see the dotted points here, which is the immersed boundary method, are very close to the purple curve here, which is this analytic expression for RPYs. So if you're looking to characterize how your immersed boundary method is likely to be behaving mechanically, I just thought this was an important or useful little trick that you can use. You could compare it analytically to the Rotny-Power Yamakawa, or you could simply, obviously tabulate. But I thought that was an interesting connection. They do draw on similar ideas about how they're approximating the fluid mechanics, but it's interesting how different communities come up with related ideas. Okay, so that's what immersed boundary particles are doing. They're essentially treating these as little blobs, and then you're spreading out the force to those local fluid parcels. And what's nice about that is in the near field, they'll become kind of a little bit sticky, but that for certain problems, like I mentioned, polymers and so on, that may actually represent better some of the physics relative to using lubrication theory or other things, where a lot of that is breaking down due to molecular level effects. Again, it's very problem specific what is the appropriate near field regularization or constitutive relations to be used. Okay. But nonetheless, it'll behave stably. All right, here's another idea using the coupling operator approaches. There's something called the Faxon relations, which are an approximation of how a colloid would respond to a flow in both its translational and rotational degrees of freedom. And so what we did here is we used a quadrature scheme on the surface of a sphere, and we basically compute the translational and angular velocity of the particle, based on the local flow velocity field. And so we get these different modalities of coupling now between two of these particles, translation, rotation, rotation, translation. And again, we can compare those to various types of asymptotic results in the CFD, in the fluid mechanics literature, namely the Rotny-Pragner tensors. And so we're going to use this little kernel, again, the Peskin delta function, spread out at each of these blue points. So each particle is this composite particle. The blue points never move relative to the center of mass or the rotational state. They're simply used for the purposes of quadrature. Okay, so I'm essentially trying to model a spherical particle through this little procedure of having an integral on the surface of a small sphere. And so what we're going to do then is we can use the adjoint conditions to leverage the Faxon kinematic relations, which tell me that the center of the translational velocity of the particle should go like this integral over the surface of the fluid velocity. This is just weighting according to the distance between the center of mass and that particular point in the fluid mechanics. So there's little blobs around each one of these blue points. So you basically just integrate the blobs over the surface, which is grabbing the local flow field using A to 0 here. And then that gets you, when you integrate it all up, that gets you an effective velocity, right, for the center of mass. And you similarly can do it for the rotational motions, and that's what's shown here. You're basically just taking the component that's in the tangential direction at the surface. And then what we can do is use the adjoint conditions now if we want an active model where we've applied forces or torques to these particles. And so the adjoint relations then give us, for whatever our quadrature scheme is, the appropriate for spreading operators so that we balance, that it's non-dissipative, that it balances what I showed on the previous slide. So you have now for my gamma, I've leveraged that to derive the lambda. And it turns out that this does a very good job in capturing the translation, and rotation couplings between these spherical particles. And so what you can do is you can compare these things to what the actual rotation and translational tensors would be, and you can see that up to about 2 radii, as long as they're not closer than 2 radii together, you basically get very good agreement with what the hydrodynamic coupling would be, given a more detailed treatment. Yeah. And similarly for the rotation. Now, of course, as you start to get close together, then these artifacts of using this approximation of blobs and so on start to come into play, and it kind of peels off from the curve as I'm showing here to sort of regularize where eventually these two particles, if they actually overlap, will start to essentially just become entrained. But if you have a relatively dilute fluid, and let's say you had a potential which kind of keeps things far apart, you could think about like charged particles, for example. This could work quite effectively in capturing your hydrodynamic interactions. Okay. And then we've also extended that in a number of other directions. And I'll talk a little bit later, if there's time, on how we've done this on 2D fluid interfaces that have curvature and where you can, again, leverage very similar ideas to come up with effective hydrodynamic coupling schemes. All right, let me just take a break for 1 minute here. So what I talk about next is how I can reduce that sort of inertial regime that I showed you before down to the kinds of things that you're maybe more familiar with when you think about immersed boundary methods, where you don't have separate momentum equations for the microstructure. They're kind of entrained to move with the local flow. I'm going to show you how we can recover that regime, starting with what I had shown in the previous slide with this Eulerian-Lagrangian kind of formulation. And then that's going to be important because we'll see that there's going to be certain terms that that come up in the method that if you sort of just started in the stochastic immersed boundary, or sorry, if you started kind of in the immersed boundary regime, it would be a little more subtle to work out where those terms come from. Okay, so I'm going to talk about these fluid structure interactions now in a few physical regimes, and this really, again, is a way that you can leverage immersed boundary ideas to build a whole wide range of computational fluid dynamics techniques and incorporate thermal fluctuations appropriately. And I would say even in the deterministic setting, there's, I think, some really interesting areas that have been a little bit underexplored, but where I think immersed boundary methods could have a really nice impact on numerical methodology. So the first thing just to notice, and this is something that is always a good exercise whenever you're developing a new numerical technique, is just to analyze some of the features of the underlying system that you're trying to approximate. And you very quickly realize with fluctuating hydrodynamics that there's sort of an immediate challenge, which is that the dynamics evolve on a very wide range of different time scales. And so that leads to numerical stiffness. And we'd like to, of course, before we go and code something up and invest many months of labor in doing that, is try to see if there are mathematical things we can do to simplify the equations, or to do some asymptotics in the physical regime that's of interest, so that we can save ourselves computational effort that may not be technically needed for that particular target application or domain. So in the spirit of that, we did a little bit of analysis of what are the different timescales, and I won't go through all of our dimensional analysis. I'll refer you to some of our papers for that. What are some of the timescales that arise in fluctuating hydrodynamics that you might not see in traditional kind of deterministic fluid mechanics, and at least as playing such a dominant role. So if you look at the timescales of the fluid relaxation, this is just done for, I guess I should say what the parameters are here, but this is basically done for logical conditions. So room temperature, water being the fluid in mind, and so on. What you'll find is that if I look at the different wavelengths of the Fourier modes of the fluid, what you'll find is that on the scale of about 10 nanometers, right? So that's getting down to length scales, of small particles. You could think about them as polymers and so on. You see that the time scale for the fluid to relax, again in that parameter regime, is going to be on the order of 10 to the negative 3 nanoseconds. So that's pretty rapid relaxation dynamics. Now, if I go and scale up to the size of, let's say, a micron, let's say that's sort of the target size of my simulation domain, you can see that the time scale for relaxation is going to be on the order of 10 nanoseconds. And so that immediately should be a little bit of a caution, because you're like, well, all right, I got 10 to the 5 if I'm doing the calculation here correctly, in terms of my fastest time scale and my slowest time scale. So that's looking not so great on some level, but I'm going to show you some ways that we can deal with that in a little bit. Traditional CFD, you might use things like implicit methods to kind of damp out those high frequency modes. It's going to be a little more subtle in the stochastic setting because those modes get excited by the thermal fluctuations. And so we're going to have to appropriately account for their statistics, and I'll show a little bit of how we do that. Now, if I look at phenomena like diffusivity, again, this is for a particle that's on the order of a nanometer, that's on the order of a nanosecond, 10 nanometers, on the order of 10 to the 3 nanoseconds. So you start to see that there's a very wide disparity of timescales. Now, there's different ways you can be dealing with this, and all it's done is you say, all right, fine, fluid mechanics isn't going to play a role. I'm just going to simply, look at the steady state of the fluid flow. And certainly that's a valid approximation, but there are problems, again, where, you might be looking at some type of dynamic scattering data that has very rapid timescale sensitivities, neutron scattering, things like that, and maybe inertial effects still are potentially of interest. Or again, there could be molecular dynamics simulation techniques that you want to interface with. And again, it's more natural to kind of do the coupling with inertial effects incorporated. And I did mention that in some cases, there are some numerical advantages of still including the inertial dynamics, even if you could treat the system in an overdamped way. That just tends to be a little bit more stable and less prone to certain types of issues. So we'll come back and we'll kind of talk about how to deal with this, but I just think it's very important to be aware that these equations are quite stiff if you try to treat them directly. So, all right, so this thermally excited, thermal fluctuations excite all the fluid modes, as I mentioned, so you really have to be mindful about how you're going to under-resolve these modes, accounting for the statistics appropriately. Okay, so for that regime 1 formulation, there's also additional sources of stiffness. I won't go into all of that. You can look at some of our previous paper for those details. But there's going to be the microstructure inertia, that coupling term that I mentioned, reduced time scales, and so on down the line. And then, of course, whenever you're doing immersed boundary methods, the actual nature of the microstructure time scales, related to its elasticity. So anyway, these are just things to be mindful of. And there's really, I would say 2 primary approaches we're going to take to deal with that. One is we can do Bayesian analysis, essentially asymptotic, on stochastic equations and try to reduce them, try to, simplify where we eliminate certain dynamics and map to, let's say, just the slower dynamics and come up with sort of new effective equations. And that works quite well to eliminate a lot of sources of stiffness. The approach that I'll talk about is how we can develop stochastic integrators that basically take into account the fact that the equations are stiff and under-resolve certain parts of the model. So I'll just start with the perturbation approach. Again, this is going to leverage tools from stochastic analysis. I'll really refer you to the papers for a lot of the details, but I just wanted to give kind of the big picture idea, which is that if I have a stochastic differential equation, as I'm showing here, I'll just lump everything into this variable z, but you can think about that as being the fluid mechanics, the microstructure mechanics, etc. There's some drift and there's some covariance term that acts on that. It turns out that there's always a PD that goes along with your stochastic differential equation. Maybe the obvious one that you're familiar with is the Fokker-Planck equation, and that's great. That governs the probability distribution. But there's also another PD that's really useful, and it turns out to be the adjoint of the operator that appears in the Fokker-Planck equation, and that is this thing called the infinitesimal generator. Without going to all the details of it, really just the main takeaway is you can write down a PD that characterizes all the statistics of your stochastic process of the form expectation if you started the process at x at time 0, let it run for a time t. If you took the expectation of this function f, I'm going to define this as u of xt. So now this f is going to be kind of like a probing function that I'm allowed to choose. It can be anything I want. Now, if I choose that's smooth enough, of course. If I choose that f, it turns out that this statistic over time satisfies the following evolution equation. At time 0, right, because if I start and I stop the process at the same time that I started, that'll just be evaluating f of x. But then as I go further in time, I get those, the averaging with respect to the process. That's going to satisfy this little PD that I'm writing here on the left. And so this is called the infinitesimal generator because it generates all the statistics. The key takeaway here is that if I know the coefficients of this partial in z, and I know the coefficient matrix of this second partial in z, I basically know the stochastic process, in a weak sense. I know all the statistics of the stochastic process. So if I know this operator, I know the stochastic process. So I can convert back and forth from a PD to the stochastic description using the link with this PD. Now, what's nice about this is I can do analysis, asymptotic analysis, in terms of this PD, instead of having to do it in the language of probability theory, which is much more intricate and technical. The nice thing about PDs, we can use fairly standard techniques from calculus essentially and asymptotics. And so what we're going to do is a singular perturbation expansion of this backward Kolmogorov PD, and we're going to make the ensembles that we can expand in this form, right? So we're going to basically have order 1, order epsilon, and so on down the line. And then the idea is we're going to take this operator A, and if you really went through and you did a dimensional analysis of your fluid equations, there would be various terms that you would expect to get small. So basically you can think of those as terms that are epsilon. And what we're going to do is split the operator into these 2 parts, a slow part and a fast part. And you can think about the dynamics. This is, again, kind of a cartoon, but it kind of captures the main idea. There's effectively often in these systems something analogous to like a slow manifold, or what in dynamical systems would be called an inertial manifold. It's a little different in the stochastic setting because you don't necessarily need to relax to that manifold, but that's basically where all of the relevant information is going to be about the state of the system on the timescales which are slow. And so you can think about a system that may be oscillated, for example, very rapidly around this, this blue set of states. So if I know where I am on the blue curve, as long as I don't move too much, and this diffusion in the perpendicular direction could be averaged over, I should be able to derive some type of PD that just describes how the state evolves along the blue curve here. That's sort of the overarching idea. And so what we're going to do is we're going to split this A into terms that involve what are slow, and I'll explain what that is in a second, and fast degrees of freedom. And so the fast degrees of freedom will basically be all the terms that come in with epsilon being 1 over epsilon, or on the order 1, as I'm showing here, and I'll say a little bit more about that in a minute. And then what we're going to do, basically your job is to arrange your PD so that you can express it in terms of an operator L2, L2 tilde, and some of the other operators that I'll show you. And once you do that, then you can make use of these theorems to essentially get what the effective slow, just on this little blue manifold, what the effective SDE is for those slow degrees of freedom. That's sort of the overall idea. The rest of this is all very technical, and I think we'll go by too quickly to really absorb, but you can refer to this paper that I did with Gil Tabak in 2015, where we explain this all in a lot more detail. So the idea is that if I know a splitting of my operator in terms of these fast degrees of freedom, if I take the operator L2, that'll look very similar to what you would have in a Fokker-Planck equation. And so if you look at the adjoint of that, I can look at what the steady state probability distribution is, and I'm going to call that psi. That's effectively just saying we've locked down the slow degrees of freedom. Let's figure out what the probability distribution looks like locked around that slow degree of freedom. Okay, and then we're going to use that to do various forms of averaging. Okay, so this is going to be an eigen, or actually in the null space, I guess technically an eigenfunction of this operator L2 star, and then we're going to choose the normalized version so that when you integrate over the fast degrees of freedom, that gives you 1. Okay, so what I should mention about all this is that splitting into fast and slow requires you to sort of classify your degrees of freedom into these two classes. Degrees of freedom that I kind of want to keep and retain, and degrees of freedom that I want to average away and basically fold into the statistics. Okay, so there's a bit of an art of how you do that in practice. Typically, the way you go about doing that is through dimensional analysis. Okay, so once you do that, you get an operator that's of this form. And then what you can do for the slow degrees of freedom, which I'm denoting ZS, so ZF is all the fast degrees of freedom, and ZS would be the slow degrees of freedom. But think of Z split into a ZS and a ZF. All of the ZFS term derivatives would be collected in what I'm calling L slow. And I'm just going to organize everything in L slow into two operators. One where I take the L slow thing that you gave me, I just average it with respect to the fast degrees of freedom, that distribution. I'm going to call that bar L1, and then anything left over, I'll just call L1 itself. Okay, so you've given slow, and I did this little process at bar L1. This is just the leftover, the little L1 bar. Okay, so then now what we can do with that is the following. It turns out that you can take the operator A epsilon, and the way that this will play out is you'll have bar L1 plus epsilon L epsilon, where L epsilon is given by this. Okay, so this is just a way of doing basically the bookkeeping. Now, if I take epsilon going to 0, and I plug in this ensemble into the operator, in other words, into my backward Kolmogorov equation, and I start comparing orders, I can start to derive equations for the U0, U1, and so on terms. And so if you start comparing orders, you find that to govern the U0 equation, that the operator that does that is this bar L1 plus epsilon bar L0. And so bar L0, if you work out, again, these balance of these terms, turns out to be given by taking the average of L1, L2 inverse, L1 plus tilde L2. And so you basically average that over the fast degrees of freedom, and the operator that you're left with only involves derivatives involving the slow degrees of freedom. And so again, I realize this is probably too quick to really give all of the details, so I'll kind of refer you to the paper for that. But nonetheless, if you organize and split the operator the appropriate way, perform this analysis to get what L2 inverse of L1 is, average it appropriately, you can actually deduce an infinitesimal generator for essentially the U0, U1 term, and reading off the coefficients then gives you a stochastic process that only involves the slow degrees of freedom. So essentially what you can do is you can start off with the full dynamics, split it into slow degrees of freedom, fast degrees of freedom, perform this averaging procedure that I've shown you here at a high level, and then what comes out is an effective set of equations for just the slow degrees of freedom, where we've averaged out over all those high frequency oscillations. Okay, so that's the rough idea. Again, I'll refer you to our paper for a much more detailed, in-depth discussion of that. Okay, so what we've done is we've applied that approach to the stochastic partial differential equations that we had when we did that inertial formulation of the mechanics. And if you do that, right, this was the original formulation of the mechanics that I showed you in the previous slide. What we'd like to do is start to get rid of certain dynamics in that equation in order to, again, make the equations less stiff before we treat them numerically. And we're going to see there's going to be some very important implications for how the thermal fluctuations play out. So using that machinery I've shown you on the previous slide, essentially that stochastic averaging approach, we're able to get a reduced system. Let's see if I can get it to now go back to presentation mode here. I thought I would zoom in because I realized that that might be a little small. Okay, so then we get the microstructure equations. Let's see, I should be able to get there quickly, don't worry. There we are. I'm trying to get fancy here, and that's, of course, what happens. So we get these microstructure equations now where, again, let me see if I can zoom in quickly. Okay, there we go. Now, what I've done here is effectively taken the mass to be small relative to the local reference fluid parcel for the microstructure. So we've eliminated, in some sense, the inertia of the microstructure, but we're still not in the tight coupling regime yet. And so if we do that, this is what the equations reduce to. What's really important to point out is because I've done everything very systematically, there is a thermally induced drift term that appears in my momentum equation for the fluid. And so that's why it's so important to kind of do this in a well-founded way, is if you just kind of cook up terms that seem intuitively right, you'll often mix some of these important contributions. And so by doing it in this principled way, we get this, that there's a contribution from the divergence of the force spreading operator here in the momentum equation for the fluid. And I don't have time to go into a lot of the details, but what's really going on here is we're using kind of a non-standard formulation of mechanics. And so the sort of the typical theorems that you would have that would tell you about the phase space and having phase space incompressibility don't hold, because our degrees of freedom and our momentum degrees of freedom are no longer kind of constant in the usual Hamiltonian sense. So you have to sort of have this metric factor in some sense on the phase space. Another interesting twist, and again, this is all this paper, is we end up doing our asymptotics using the total momentum of the system. And so this P actually is account for not only the momentum of the fluid, but also of the microstructure. And it is necessary in order to do that to push the asymptotics forward. Otherwise, there's an additional interesting time scale that enters into the problem. And so in asymptotic limit, you realize the immersed boundary method, in some sense, its fluid velocity field is doing double duty. It's basically the momentum equations for the microstructure simultaneously with the fluid body. Okay, so that was one of the insights that came out of this analysis, and what I'd like to point out. Now, in order to get into the physical regime that closely corresponds to the immersed boundary method, we're basically going to take this epsilon parameter now to go to infinity, right? Because this has slip in it still. And so if we do that, all right, so I've already pointed out the, just bear with me 1 second here. There we go, all right. That will result now in this regime. Oops, here we go. There we are. Yeah, and so that will result in this regime here, where now the coupling has been tight, and then now we're reduced to this set of equations. And it looks very closely to the original formulation of the stochastic immersed boundary method. But again, doing that sort of principled reduction shows that there's actually an additional thermally induced drift term in the fluid momentum equation that's given here based on the force spreading operator. Okay, and so in this case, now we no longer have the inertial of the microstructure being accounted for in P total. P total is basically of the fluid, and then the microstructure is in some sense enslaved to move at the same velocity as the local fluid parcels. And that's really closely related to the traditional immersed boundary formulation. And so that's what I meant about the fluid equations, in some sense doing double duty. And so that's one of the really nice, elegant aspects of the immersed boundary method, is you eliminate needing those extra inertial momentum equations, and that leads to a lot of computational advantages and efficiencies. And so that's what's being written here in a slightly non-standard form, because I'm using the momentum of the fluid field, P here, instead of rho U. But you could just put rho U here and everything would reduce to the familiar form of the immersed boundary system. Okay, and then the thermal forces come out of that, and it simply reduces in this case now to negative 2 kBT L. It's just that there'll be an additional drift term that we have to take into account. And then, we can go one step further, which is to also take now essentially the viscosity of the fluid to be large. And we can now derive a sort of overdamped version of the immersed boundary method. And this is closely related to the method of Stokes-Litz and Stokesian and Brownian dynamics. And if you do that, this is what you end up with, where now this H, which I'm calling H SELM, but just for the Eulerian-Lagrangian nature, but you can think about this as just being an immersed boundary mobility tensor, where you spread your force from wherever your particles are, compute the steady state Stokes flow, do your velocity averaging. This is my shorthand for that, for spreading, Stokes solver, velocity averaging. And now you can get hydrodynamic coupling tensors. Remember what I was talking about, some of the colloidal formulations that are done in CFD community. This provides an immersed boundary approach to basically getting those effective hydrodynamic coupling tensors, along with the appropriate thermal forcing, which again comes in with the correlation structure being the same as that coupling tensor, 2 kBT. This is also known as the mobility, but a very important, again, due to all those non-standard conjugate variables that I mentioned, you end up with a divergence of that mobility kBT, which is important so that the overall system exhibit appropriate equilibrium statistical mechanics. So proceeding in this kind of principled way, we can now derive these stochastic immersed boundary methods, these different regimes, starting from the inertial regime all the way through to the overdamping, where we've eliminated the fluid dynamics, or at least the direct dynamics of the fluid. We still have the fluid coupling in the system. And so I think there's a lot of potential avenues to explore interesting ways that you can leverage immersed boundary ideas to create different types of solvers, not only in the stochastic case, but also in the deterministic case. So you can imagine if you were in a very complex geometry, microchannel in like microfluidics, something like that, or some other environment where you have lots of obstacles, you can model those with immersed boundary points, and you can compute effective hydrodynamic things quite readily using fairly standard solves from immersed boundaries. And so I thought that was kind of maybe an interesting thing to point out of how these techniques relate some of these different approaches in CFD. So anyway, you can go to look at our paper for details of how we've derived each of these regimes. And we'll mainly be talking about this regime here, which is where we've reduced the inertial, we've eliminated the momentum for the microstructures. Okay, all right, so let me move forward just with the remaining time to talk a little bit about how we're going to deal with now spatial and temporal discretizations and this leveraging this idea of fluctuation dissipation balance. And as I mentioned, this goes back to work I started as a postdoc with Pete Kramer and also continuing to collaborate with Charlie Peskin. So if we go to that regime where we've eliminated now the momentum of the microstructures, we reach to this area that's closely related to our original formulation of the stochastic immersed boundary method. And so the idea is, again, we can leverage fluctuation dissipation ideas to obtain these flow equations. Okay, so then if you work out what the thermal forcing is, the thermal forcing is going to be given by this, okay? And this basically comes from the previous slide. I'll just mention there's an additional drift term as well, which I've denoted here as F drift. And if you use the Peskin delta functions, this is the form of that divergence term. Okay, so let's see. I realize I'm getting up towards the end of the time here. So the other question that was asked earlier, and this is important, is that when you start discretizing these equations, again, you do want to have consistency with statistical mechanics. And this is just a very quick illustration showing that when you start dealing with adaptive meshes and like even uniform mesh, depending on your discretization scheme, you have to be mindful of how you stochastically force the system. And so this is just showing vertically the eigenvalues of the Laplacian, which is kind of well known in CFD that you will get less dissipation if you use something like central differences to approximate the Newtonian stress relative to if you were to do, the continuum mechanics. Essentially, because of, aliasing artifact, if you do central differences, you'll find that, in Fourier is essentially like cosine of a wave number, and you have for the continuum Laplacian, right? You're going to have something that scales roughly like the wave vector, wave number rather. So, in other words, the true Laplacian, in some sense, has a much stronger rate of dissipation than your empirical Laplacian. And so, if you were to force just using the continuum formulation, you'd way overforce your high frequency to junk, because basically you're just going to have the simulation. So really important you balance those, but again, you can leverage that fluctuation dissipation relation that I been done here. And if you do that, not only can you control for artifacts like this, but also if you have things like adaptive mesh refinement, we've done a fair amount of work showing you can derive in a principled way thermal forcings that take into account the discretization artifacts. So if you were to use kind of a phenomenological approach, you'll get kind of these long spurious correlations. If you use sort of this fluctuation dissipation balance approach that we've used, you'll get these kinds of nice null-controlled fluctuation. Again, taking into account the dissipation of the discrete operator. So I'll just refer to our papers for details on those very. Push this in a number of directions, including adaptive meshes, finite elements, and more recently been working also on meshless approaches. Okay, let's see here. So I know I'm kind of running out of time. I might just skip the stuff on stiff numerical integrators. Again, I'll refer you to our 2007 paper if you're interested in that. So, for the stochastic immersed boundary method, even though I've eliminated the inertia of the microstructure, there's still disparate timescales in the excitations of the fluid mechanics that have to be grappled with. Because, the ultimate object of study is the figure of the microstructures for the most part. And so what we'd like to do is under-resolve the high-frequency modes of the fluid. And what we've done is developed exponential time-stepping techniques, which I won't really have time to get into today, but the idea is that rather than treating this using kind of a traditional finite difference in time method, what we're essentially leveraged is the fact that this equation is effectively got a dissipative part, which is linear. And so if you were to use the method of integrating factors, formally, you could rewrite this fluid equation as this exponential expression. And then I can use tools from stochastic analysis essentially to compute random variables for these parts that involve the increments of Brownian motion or the Wiener process. This is the same thing as my dW before. I've just switched notation slightly to dBt. But anyway, I won't go into all the details, but there's a analytic procedure you can use to do that. And with a few approximations on how the force evolves over time, the time scale that you're resolving, namely treating it as constant, although you could use other quadrant schemes, we effectively can work out both for the fluid equations integration as well as the microstructures integrations. We can work out what the effective statistical contributions are over that scale. So that basically the scheme, I'm just going to go to the summary of it, which again, I don't want people to absorb this on the fly, given how quickly I'm going. Basically this tells you how the fluid updates over that time scale delta t, how the microstructure evolves over the time scale delta t, and now you've gotten rid of the stability constraint from those high frequency excited fluid modes. So now stability and accuracy are going to depend now primarily on the microstructure evolution. And so I'll refer you to our paper for those details, and these are all the gory details of how you generate the appropriate Gaussians. Don't worry, you don't have to implement all of this. I have software, and I'll talk about that in a future session discussed. So you could leverage a lot of these results without having to go through all of the hard work and tedium that we've gone through all this to work in practice. So anyway, this just shows if you under-resolve, you can get good results and capture things like hydrodynamic correlation and the auto correlations of particles and so on. Yeah, I do realize that I'm on the boundary of time, so I think I'll end with just a few simulations. I think Charlie mentioned some of the previous lectures about immersed boundary methods preserving topology. So one fun thing you can do is that have interesting topology. This is showing thermally fluctuating polymer knot here. And because of the nature of the immersed boundary method, referencing an uncommon like each of the microstructure degrees of freedom referencing a common flow field, at least up to particle precision, the discretization error, truncation error, you're going to have that the solution is effectively a homeomorphism, topological constraints. And so there's all kinds of fun things you can do with topology without needing to have very explicit excluded volume interaction terms. And this is just showing osmotic pressures of a confined polymer knot as you, the arc length fixed, radius fixed, but you use topology, you get this significant drop. So that's just a fun little demonstration of that idea. We've also did immersed boundary methods towards those microstructure problems, able to do rheological studies. So we basically have a version where there's shear interactions at 3, or in other words, you can think about your sample that you're simulating as being immersed in a bunch of boxes that are shifting. And this is a little your material rheometer. And then what we can compute using Irving-Kirkwood relations, effective stresses from the microstructure. And this really gets to that overall motivation of how do sort of larger scale mechanics emerge from the detailed microscale interactions. And this is just showing such a simulation where we've polymer solution, worm chain, and not sure if it'll play here, but basically what this is do is simulate using the sliding bricks model. And what you would end up with is the ability to compute out from the nature of that microstructure what the corresponding macroscopic stress law. So what you can do from it is you can derive the effective stress strain relationships, or really the effective stress strain rate relationships, the complex fluid. And that's what's shown here. And if I showed you would see that things break apart in this, which leads to a big climb in the stress. But then over time, once you equilibrate, you basically get to a configuration where it's lining up with the direction of shear. The thermal fluctuations kick you out of the direction of shear, which then stirs the polymers, and you end up with an effective steady state shear response. So depending on the time scale you were to interact with this material, you would get different types of stress responses. And so that's really important if you're trying to do constitutive modeling of a much larger scale material. Often it's not completely obvious what that sort of applied shear rate stress response should be. So this is a way that you could numerically tabulate or maybe even deduce constitutive laws for larger scale mechanics from simulations. And I think this would be a really nice, or more if people are interested in using these stochastic immersed boundary ideas. And there's a lot more I could stochastic immersed boundary methods. I think this is probably a good place to leave it. Thank you. Great to be here and discussing this with everybody.